All right, remember our goal here is to simplify this down to a single power of a single trig function, okay, like we were doing yesterday. There's actually a strategy in this problem that we haven't quite talked about yet, which is maybe why y'all are stuck. But here's what I can do, just for the sake of doing something. You see that second term, it's sine over cosine? Everyone see that? That should be jumping out at you now. That should be slapping you in the face saying, hey, I'm something. I'm an identity. What is sine over cosine? It's tangent of x. So I could call that tangent of x. That might seem like a step in the right direction because I got rid of two trig functions and replaced it with one. Now the question over here is, do we have anything? Is 1 minus sine of x equal to cosine x? No, but 1 minus sine squared of x is equal to cosine squared of x. That's true. That's baby PID number 1, okay? So what can I do in that first term? Well, let me ask you this. Can I split up the denominator? Can I call it cosine of x over 1 minus cosine of x over sine of x? Is that legal?
Yeah.
No. You cannot split up denominators like that. If it were numerators, you could. If it were 1 minus sine of x over cosine, you could call that 1 over cosine minus sine over cosine. That works. That works. You can split up numerators, but you can't split up denominators. So let me go ahead and I'm going to leave that there as a warning. So I do have minus tangent of x, but I have cosine over 1 minus sine of x. So here's my little strategy, and this is a new strategy for you. If the bottom were, in fact, 1 minus sine squared, I could call it cosine squared. What can I do then to turn it into a 1 minus sine squared legally? Well, I can multiply by a clever form of 1. Is it okay to multiply something by 1? Yeah, it doesn't change its value. What would I need to multiply by in the bottom to turn 1 minus sine of x into 1 minus sine squared of x? No, if it's just sine of x and I distribute, I get sine of x minus sine squared, not 1 minus sine squared. Close, not 1 minus sine of x, but 1 plus sine of x. Peyton saw this yesterday, though difference of squares, right? 1 minus sine squared is a difference of squares. This right here you need to recognize as a difference of squares. And how do we achieve a difference of squares? We multiply two things that are what's to each other? Conjugates. Okay? Anything times its conjugate is a difference of squares. So here's the strategy. Whenever you see 1 minus sine of x or 1 minus cosine x or 1 minus any function, or even 1 plus sine of x, 1 plus cosine of x, multiply by the conjugate over the conjugate. That's a new strategy. A new strategy. Multiply by the conjugate of something over the conjugate of something. A new strategy. That's equal to 1. Now, let's see what happens in the bottom. 1 plus sine of x times 1 minus sine of x is 1 minus sine squared of x. Now, in the top, don't distribute. We don't want to expand out the top. We want to leave it factored because the whole reason we multiplied by the conjugate was to expand the denominator, not the numerator. If we leave the numerator factored, we can eventually divide out common factors. And of course, I still have minus tangent of x. Now, the whole reason we multiplied by the conjugate over the conjugate is so we can set up a Pythagorean substitution. What's another name for 1 minus sine squared? Cosine squared. That's going to be a very, very familiar form of baby PID number 1. 1 minus sine squared is cosine squared. 1 minus cosine squared is sine squared. And that's still over 1 plus sine of x times cosine of x. And then it's still minus tangent of x off to the side. Now, what can we do in the first term? Do y'all see anything happening? We can divide out one of the cosines. And we're just left with 1 plus sine of x all over cosine of x. Now, my question to you is, do I want to leave it as minus tangent of x in the second term? Look at what it started as. It started as sine over what? Sine over cosine. If I leave it as cosine in the bottom, Then I have common denominators. I can combine the two terms. Yes, yes? So I'm going to put it back as sine of x over cosine x. So tangent was a step not necessarily in the wrong direction, but my insight tells me I should put it back. Now, since I have a common denominator, I can put the whole thing over the common denominator and say it's 1 plus sine of x minus sine of x. And now what happens with your sine of x's? They cancel or subtract out, either one, and you're left with 1 over cosine of x. Now, what's another name for 1 over cosine of x? Secant to the first power of x. Did we simplify it down to a single power of a single trig function? Absolutely. Now, you know what we created? If you look at this original expression up here, this entire original expression is really just equal to secant of x. That's a new identity. Do you want to memorize that identity? Say heck no. Heck no. We don't need to memorize that identity, because if we need it or we need to prove it, we could just do so by using the identities we've already learned, the fundamental ones, and a little bit of algebra. So there you go. That's how you do that one. So maybe you didn't know to do that when I gave it to you as a warm-up, but now it's in your arsenal. It's a tool in your tool bag. You need to be aware that it's possible and look for opportunities to multiply by the conjugate over the conjugate. When you do so, you set up a difference of squares, and the difference of squares sets up a Pythagorean substitution. So that's why we do it. Okay, let's do that again. Conjugate over conjugate sets up a difference of squares, and the difference of squares sets up a Pythagorean substitution. All right, that's why we do it. All right, any comments or questions on E? E for exciting, E for exhilarating, E for easy? Maybe not easy. E for fun? That doesn't quite work, but sure, we'll go with it. Exhilarating, exciting, excrement, amazing. There you go. Amazing. Letter F. Erase it? Okay, first of all, notice that our variable is not theta. The variable is not x. Our variable is beta. Our variable is beta. Is that okay? It's just another variable. It looks like a capital B on a pogo stick. It's kind of a fun variable. It reminds me of Tigger from Winnie the Pooh. But here's what else I'm going to notice. I noticed that my angles are not the same. I have 3 different angles. They all have beta in it, but there's 3 different angles. One is negative beta, one is positive beta, and one is pi halves minus beta. So here's the new strategy. Get the angles the same. That should be goal number 1. If your angles are not the same, you cannot use the identities to combine things. It does no use to try to combine them. They're different functions. If the angles are different, they're different functions. So let's try and get the angles the same. Let's look at the first one. Tangent of pi halves minus beta. What's that equal to? Cotangent of beta, right? That's the cofunction identity. Thank you, Lawson. That's the cofunction identity. Tangent of pi halves minus beta is equal to the cofunction cotangent of beta. So that takes care of that one. Okay, the next one, cosecant of negative beta. The question is, do I forget about the negative or bring it out front? Is cosecant even or odd? It's odd. So what do I do when it's odd? Bring it out front or get rid of it? Bring it out front. Now I got to be careful when I bring it out front like this, because I just turned that multiplier into subtraction. So I better put parentheses around it so it stays multiplied. You don't want it to turn into subtraction. And then the bottom, I do have beta, so I can just leave it as beta. But cotangent squared of beta plus 1, isn't that equal to something? It's a squared one after all. The squared ones possibly could be the PIDs, right? Didn't we learn that 1 plus cotangent squared of x is equal to cosecant squared of x? Didn't we learn that? Isn't that what we have in the bottom? Isn't cotangent squared plus 1 the same as 1 plus cotangent squared? Yeah. So would it be worth replacing it with a single trig function? Getting rid of two terms and writing it as one term? That's for sure, because then we can divide out common factors. So yes, the angle is already beta, so I'm going to go ahead and call that cosecant squared of beta in the bottom. So that's what I did on my first line. I did a little bit of something in each of the three factors. Okay, now, on the next line, what's the negative times the negative? A positive, so I just have cotangent of beta times cosecant of beta, and in the bottom, I'm going to write cosecant squared as cosecant of beta times cosecant of beta. Why would I want to do that? What happens with one of my cosecants? They divide out. And I'm just left with cotangent of beta all over cosecant of beta. Is that our goal? Did we want to get down to that right there? Are we done? Nope. Our goal was to get it down to a single trig function, a power of a single trig function. So, is this one of the ratio identities that we learned? We learned sine over cosine is tangent, and we learned cosine over sine is cotangent. We never learned one with cotangent and cosecant, did we? Nope, because there's two negatives. We multiplied negative times negative, and we got a positive. That's why it's important to realize that that second term was multiplied, not added. Okay, here's another strategy. If you're not sure how something simplifies, okay, and we talked about this yesterday, put everything, when you're stuck, put everything in terms of sine and cosine. We don't want to go back to the definitions in terms of x, y, and r. Don't go that route. We only did that to prove the fundamental identities. When we're proving other identities or simplifying, we want to stick with the trig functions, not their definitions. So don't call cotangent x over y and cosecant y over r, or r over y. Let's just put it in terms of sine and cosine. So cotangent is cosine over sine. There's the numerator. All over cosecant is 1 over sine. Yes, yes? Cotangent is cosine over sine. Cosecant is 1 over sine. All right, now remember what I said yesterday too. When you get a complex fraction, you should cheer. Hooray, hooray, right? We got a complex fraction. Because what's the next step? Always algebraic when you have a complex fraction. Stay, change, flip. Stay, change, flip. Or lick them over, lick them. Let's do stay, change, flip because the denominator is a single factor. So I get cosine of beta all over sine of beta times sine of beta over 1. And what happens with your sine of betas? They divide out, and we're left with cosine of beta over 1. What's anything divided by 1? Cosine. You could skip that step if you want. Cosine of beta over 1. You could skip this step. We're left with cosine of beta. Are we done? Yep. That whole thing up there is equal to cosine of beta. This whole thing is cosine of beta. That's a new identity. Do you want to memorize that identity? No. Factor, no. Nope. Okay. The only difference between what we're doing now and later on when we proof is later on when we proof, I'm going to tell you it's equal to cosine. It's actually easier because you have a definitive target. Right now we're just kind of vaguely going towards a single power of any trig function. We don't know which trig function it's going to end up being. We don't know what power it's going to end up being. But when it's a proof, I will say prove this. Prove that that equals cosine of beta. And now you have a definitive target. You work on the left side until you get all the way down to cosine of beta, and then you say you're done. Yeah. Has it been 15 minutes? Yeah. Okay. Yeah, it's been 19 minutes. Okay. Any questions on simplifying? Kind of fun, right? You're learning new skills. All right. The next thing that we need to be able to do is to solve. We're going to learn how to solve trigonometric equations. All right. So the first thing we're going to do on all of these is we're going to solve between 0 and 2 pi. This is our comfort zone. This is within one positive rotation. That's where we like to live. And then we're going to extend it from 0 to 4 pi. That's 2 positive rotations. And then we're going to extend it from negative infinity to infinity, which is all solutions. Oh, crap. Okay. But let's start with part A. Find all the solutions to this between 0 and 2 pi. So our variable is x. We're looking for all solutions between 0 and 2 pi. So 2 times the sine of some angle squared plus the sine of that angle equals 1 for some angles on the unit circle. Bless you. Does anyone know what that angle is just by looking at it? The sine of some angle squared times 2 plus the sine of that angle equals 1. Should we do trial and error? Should we do guess and check? Does pi 6 work? Does pi thirds work? Does 3 pi fourths work? No, we should probably have some kind of strategy. What strategy are we going to use here? Well, we're going to tap into the fact that we've solved polynomial equations in the past. If this were, let's say if this were 2x squared plus x equals 1, how would you solve that? How would you do it? Like, what would you do first? If you factor out the x, you can't set both factors equal to 1. That only works when it's equal to what? 0. So you would set it equal to 0. You would say 2x squared plus x minus 1 equals 0. And now that you have it equal to 0, you would do what with this quadratic trinomial? You would double bubble factor it, right? And since the leading coefficient isn't 1, it's one of the fun types. It should be a 2x and an x. 1 is prime, so it's got to be a 1 and a 1. You got to have a middle term that's plus 1, so it's got to be a plus and then a minus. You would do stuff like that, right? You would factor it like that. And then you get x equals 1/2 or x equals -1, and you'd be done. That's how you would solve it if it were really just 2x squared plus x equals 1. Well, guess what? It's very similar to that. Except instead of x, we have sine of x. Instead of x, we have sine of x. It works the exact same way. This is nothing more than a quadratic trinomial in terms of sine of x. That's it. So we're going to solve it the exact same way. So let's come over here. I'm going to bring everything to one side. I get 2 sine squared of x plus sine of x minus 1 equals 0. And then we're going to factor it. Double bubble factor it equals 0. Instead of 2x minus 1, it's 2 sine of x minus 1. Instead of x plus 1, it's sine of x plus 1. And now that they're both factored equal to 0, I can set them both equal to 0. So 2 sine of x minus 1 equals 0, or sine of x plus 1 equals 0. And then I solve both of them for sine of x. I get sine of x equals 1/2, or sine of x equals -1. Now up here, if it were just in terms of x and not sine of x, we'd be done at this point. X equals 1/2, x equals -1. But we haven't solved for x yet, have we? We solved for sine of x. So that's your first step. Solve the trig function. Once you get down to the trig function equals a number, now it's unit circle time. It's unit circle time. What time is it? Unit circle time. We got to know within one rotation what angles and radians does the sine equal 1/2? Pi 6, and what's the other one? 5 pi 6. Very good. That's quadrant 1 and 2. Quadrants 1 and 2. Pi 6 and 5 pi 6. And then the other one, or where is sine equal to -1 within one rotation? Not 2 pi thirds. 3 pi halves. You had it flipped. It's straight down, due south, right? Due south, way down here. And this one was over here, here, and here. Okay, so there's the answer to part A. There's all the solutions between 0 and 2 pi. There's 3 of them.
You want negative?
Not yet, no, not yet. It says right here between 0 and 2 pi. That's within one positive rotation. Now, if it had said between -2 pi and 2 pi, then that would be one negative rotation as well. But the next one, part B, says between 0 and 4 pi. So for part B, Are all three of these angles going to still be in the interval from 0 to 4 pi? Yes. We're going to have pi 6, leave a little space. We're going to have 5 pi 6, leave a little space. And then we're going to have x equals 3 pi halves and leave a little space. All I need to do to get the next ones that are within the next rotation is find all the ones that are what with these? Coterminal. We just need to add a full rotation to them, don't we? That's all we need to do. Get these and then add a full rotation to them. So what is pi 6 plus a full rotation? No, you don't add 6 pi 6 to it. That's a half rotation. Sillies, one rotation is 2 pi, which is 12 pi 6. Be careful. So 12 plus 1 is 13 pi 6. Sillies. Y'all are silly. You added a half rotation to it. All right, what's 5 pi 6 plus 12 pi 6? 17 pi 6. Yeah, now over here we're counting by halves. So one rotation is 2 pi, which is 4 pi halves instead of 12 pi 6. So what's 4 pi halves plus 3 pi halves? 7 pi halves. So there you go. If I wanted all the solutions between 0 and 6 pi, you would just add another rotation to 13, 17, and 7. Okay? So that's part B, all of them between 0 and 4 pi. Now, how many solutions are there going to be from negative infinity to infinity? There's infinitely many. Holy cowabunga crap. Are we going to be able to list all of them? No, we're not. We can't list infinitely many. But here's what we know. All of the angles that are going to work are going to be what with those three highlighted angles? They're going to be coterminal with them, right? So here's what we're going to do. If you list all of them from negative infinity to infinity, you're going to list them as equations. You're going to say x equals pi 6 plus, how do we get all the coterminal angles? They're multiples of what? 2 pi. So we're going to say 2 pi n. And then we're going to say the next one is x equals 5 pi 6 plus 2 pi n. And then we're going to say the last one is 3 pi halves plus 2 pi n. And then at the back here, I'm going to put another comma and say, oh, by the way, n is an integer. You don't have to say it after each one. You can say it after you're done with all three of them. It has to be an integer. If it's not an integer, we're not going full rotations. Now, we don't have to say plus or minus 2 pi n because n is an integer. N could be -1. And if we're talking about -1, we're subtracting. N could be -2. That would be subtracting 2 rotations. So we just need to say plus. And there they are. So that's how you do these problems. You solve for the trig function first, and then you use the unit circle to find all of them within one positive rotation. That's your comfort zone. And then if we need to find others, they're just coterminal with them. Okay? Trig equation. We're doing that right now in BC calculus. We're finding polar area of polar curves, and we need to figure out what the solutions are. Let me just kind of show you what we're doing here. A polar curve might look something like this. It might start here, and it comes in, and it has this inner loop, and looks like that. We call this a limison, which is French for snail. We're interested in finding the area of this inner loop right here. So what we need to know is for what angle do we rotate, do we hit the 0 right there? Because if I know when the radius is 0, I can just find the area by looking between consecutive origin points. So we have to solve our equations by setting them equal to 0. That's where the radius is equal to 0. So we're doing this right now in BC calculus. So it's important that we learn how to do it here so that if we need it in a larger context moving forward, we know how to do it. Does that look like a snail to y'all? Someone looked at it one time and said, snail, and they were in France. Limousin. Not escargot. That's the snail that you eat. Limousin is the snail that you draw on the coordinate plane. The snail you don't eat. Okay, let's move to example 8. Find the solutions to cosine cubed of x over sine of x equals cotangent of x such that the solutions, here we go, Peyton, are between -2 pi and 2 pi. So now we're going back a negative rotation. So here's my goal. I'm going to find all the ones first between 0 and 2 pi, and then I'm going to go backwards. Then subtract a full rotation. I got to have a strategy. Find all of the ones in our wheelhouse between 0 and 2 pi, and then subtract the full rotation to get the others. Now it says, be careful not to lose any variable information in the process, like the cotangent of x. All right, make sure your final answers are in the domain of the equation. Okay, all right. Lots of warnings here. Now, notice we have three trig functions, cosine cubed, sine of x, and cotangent of x. I know that sine of x can't be 0. Would y'all agree? If sine of x is 0, then I'm dividing by 0. That doesn't work. So here's what you do. If you have things on both sides, your first step should be like what we did in the previous problem. Get everything on one side and set it equal to 0. Now, the goal of setting something equal to 0 is to factor it. And the first rule of factoring is to look for a common factor. Do we have any common factors yet? No, we don't. So here's what I'm going to do. I'm stuck already. I can do the same strategy here that I did on my simplifying. I can put everything in terms of what? Cosine and sine. Yeah, so this one's already cosine over sine, so that one's good. But what's another name for cotangent? Cosine over sine. Oh yeah, oh yeah. That's already looking prettier because now I can combine them and put it all over sine of x. So I get cosine cubed of x minus cosine of x. Now here, since I have a single fraction, this is what we're looking for. I have a single fraction. Whenever you have a numerator over a denominator, and you want to know where it's equal to 0, that's going to happen when which one of them is 0. This is an important idea. When the numerator is 0. Okay? That's a very important idea. 0 over 5 is 0. 0 over 10 is 0. 0 over 100 is 0. If you have a single fraction and you want to know where it's 0, all you got to do is set the numerator equal to 0. As long as the denominator is not 0, the denominator cannot be 0. We already said that in the beginning. Sine of x can't be 0. So let's go ahead and set it equal to 0, the numerator. Cosine cubed of x minus cosine of x equals 0. But I'm going to put a little note to myself that sine of x can't be 0. In other words, if I solve the numerator and there happens to be a value in that solution set that also makes the denominator 0, I got to toss it out of the domain. I got to toss it out of the solution set because it's not in the domain. Okay? All right, so now we can focus algebraically on this. It's equal to 0. So the whole point of getting something equal to 0 again is to factor it. And what's the first rule of factoring? Look for a what? Common factor. Yeah. Do we have a common factor? Cosine. So I can pull a cosine out, and that leaves me cosine squared of x minus 1. Ooh, cosine squared of x minus 1. Isn't that equal to something? Yeah, let's come off to the side and see what that's equal to. I know that 1 minus cosine squared is equal to sine squared. I know that 1 minus cosine squared is equal to sine squared. So what would cosine squared minus 1 equal? It's a little different, right? Negative sine squared. Yeah, if you multiply through by negative 1, you get negative sine squared. Is that worth a replacement right there? I like it. So I get cosine of x times negative sine squared equals 0. Now, if I pull that negative out front, I get negative cosine of x times sine squared of x equals 0. Can I multiply both sides by negative 1 to get rid of it? Is it legal to multiply both sides by negative 1? Yeah. So now I just get cosine of x times sine squared of x equals 0. And I have it completely factored. Guess what I do now? I said both factors equal to 0. So cosine of x equals 0 or sine squared of x equals 0. Yes, yes? All right. So now it's unit circle time on the first one. Where between 0 and 2 pi is cosine equal to 0? No, cosine of pi is negative 1. 2 pi? Cosine of 2 pi is positive 1. Pi halves, and where? and 3 pi halves. Yeah. Okay. Now, that's between 0 and 2 pi. What else do I need to do to get the ones that are between negative 2 pi and 0? Now I need to subtract a full rotation. So what's pi halves minus 4 pi halves? In other words, I want this one here and I want that one there. So yeah, negative 3 pi halves and negative pi halves. So those are all the ones now that are between negative 2 pi and 2 pi. I find the ones between 0 and 2 pi, and I just subtract the rotation. Now, let's focus on the second one. It's like its own separate problem. Is it okay to take the square root of both sides? Yeah, it actually is, right? As long as we remember plus or minus on the other side. As long as we remember plus or minus on the other side. But what is plus or minus the square root of 0?
0.
0. Now, where is sine equal to 0 between 0 and 2 pi? 0, pi, 2 pi, and then there would be negative pi and negative 2 pi. Holy moly, 5 solutions? So do we have 9 solutions overall? Okay, you might think so, but remember, it says make sure your final answers are in the domain of the equation. What did we say in the very beginning? Sine of x can't equal 0. I said that there. I reminded myself right here. So is it even worth solving this equation? When I have sine of x equals 0, is it even worth solving it? No. None of those guys are in the domain of the function. Ah, surprise, surprise. They're trying to sneak into club solution. They know it's good in club solution. But we're the bouncers at the door, and we don't let them in. So guess what the solutions are? If you want to write your solution set, you can do old algebra 2 style, x epsilon, pi halves, 3 pi halves, negative 3 pi halves, and negative pi halves. I'm okay if you just leave them listed like this too. Either way. The bottom one is a fancy one. It's the solution set, the set of solutions. But x equals, and that's fine, as long as you have x equals. Now the other ones, if you left them exposed, I would think you're trying to include them. So you either draw a line through your 5 solutions there, or you leave sine of x equals 0 and draw a line through it. Either way, you're telling me or you're acknowledging that those aren't even in the domain. All right, so that one was a little more fun, wasn't it? Let's review what we did there. We had variables on both sides. So we got everything on one side. We set it equal to 0. We had a quotient on the first term, so we used the quotient or the ratio identity for cotangent. That gave us a common denominator. We got it down to a single fraction. When you have a single fraction and it's equal to 0, you set the numerator equal to 0, so long as the denominator is not. Pulled out a common factor, used an identity, and then solved. And then made sure our answers were in the solution set or in the domain. All right, when we ultimately test over this section, there's going to be 3 sections to the test. There's not going to be any multiple choice on the next test. The first section will be doing proofs. The middle section will be solving equations like this. And the last section will be more proofs using different identities. Okay? So we need to know how to solve equations in a specified interval, negative 2 pi to 2 pi. All right, any questions on number 8? We have 12 minutes left. Let's do one more. Let's do one more and we'll call it a day. Algebraically find all the solutions to this equation. All of them. Well, guess what my strategy is? I'm going to find the ones between 0 and 2 pi. And then just say plus 2 pi n. Is that okay? Find all the ones within one positive rotation, and then just say plus 2 pi n to the end of them. All right, let's look at example 9. I have a tangent on both sides. Is it okay to divide the tangent out from both sides like that? Why not? That's not okay. Be careful not to lose any variable information in the process. If you ever lose variable information from an equation, you're losing solutions. So don't do that. My first step, since I have variables on both sides, is to get everything on one side and set it equal to 0. Once it's equal to 0, our goal is to factor it. What's the first rule of factoring? Common factor. Is anything common? The tangent. So I'm going to pull the tangent out, and that leaves the square root of 2 cosine of x minus what? 1. When you factor it out of itself, you're left with 1, not 0. All right. Now I have it factored. Can I set each factor equal to 0? Yeah. So I get tangent of x equals 0, or the square root of 2 cosine of x minus 1 equals 0. We're already at unit circle time for tangent. Where is tangent equal to 0? Pi halves and 3 pi halves. Is that right? I think those are the vertical asymptotes, don't you? Oh, pooper scooper. Yeah, it's 0, pi, and 2 pi. 0 pi and 2 pi. Now, I don't really need 2 pi because it's coterminal with 0. So I'm just going to go 0 and pi. 2 pi is actually the start of the next rotation. You got to be careful. Okay, now the next one is not quite ready for the unit circle. I got to solve for cosine. So if I bring the 1 across, I get square root of 2 cosine of x equals 1. And I divide through, and I get 1 over the square root of 2. And if I rationalize the 1 over the square root of 2, I get the square root of 2 over 2, which makes it now a recognizable unit circle ratio. Yes, yes? Now it's unit circle time over here, UCT. Where within one positive rotation is cosine equal to square root of 2 over 2? Pi fourths, and what's the other one? 7 pi fourths. Good, quadrant 4. So notice I have 4 solutions within one rotation. 4 solutions within one rotation. I wanted all the solutions, right? So that's easy now. So I could say the solutions are going to be x equals 0 plus 2 pi n, pi plus 2 pi n, pi fourths plus 2 pi n, and 7 pi fourths plus 2 pi n. And then I'm going to say comma where n is an integer. You just say plus 2 pi n at the end of them. That gets you all of them. Those are the equations that generate the rest of them. Now notice pi fourths and 7 pi fourths, they're not a standard distance away from each other, are they? They're not a uniform distance away from each other. But look at 0 and pi actually are. 0's over here and pi's over here. Aren't they just a half cycle away from each other? So you can't always do this, but in this case, if you want, instead of saying 0 plus 2 pi n and pi plus 2 pi n, you can combine them and just say 0 plus pi n. And that'll land on all of them, won't it? Start at 0 and just go a half rotation, and that'll land on 0 pi, 2 pi, 3 pi, 4 pi, 5 pi. You can't do that unless it lands at a quadrantal angle. You can't do that for pi fourths and 7 pi fourths because they're not a half rotation away from each other. But if this were a multiple choice question, maybe I don't have 0 plus 2 pi n and pi plus 2 pi n. I just have x equals pi n plus the other two. So you could also say x equals pi n, and then the other two, pi fourths plus 2 pi n, and 7 pi fourths plus 2 pi n, where n is an integer. That would be like a multiple choice question. Free response question, you can stop right there with both of them. Every answer within one positive rotation plus 2 pi n. All right, that's enough solving for today, huh? I want it to soak in. We'll start tomorrow with example 10, and then we'll breathe a sigh of relief, it says. Phew. Sigh of relief. PSI. Pounds per square inch. Any comments or questions on today's lesson? Was it a good one? We got to example 9. How far did we get? We got example 6E, 6E through 9. 6E through 9. That's not bad. That's all in a day's work, huh? Okay. Make sure you're working on your homework. You don't save it to the very end. You're reinforcing the skills we do in class, and you're not having to just force it by copying the key the day before it's due. Homework is still the #1 most important thing you could do to master these skills. Guess what the #1 thing students tend to not do? Their homework. Bad, bad, bad habit.